In this video, we solve problem number 1 from quiz number 6 from the fall 2020 semester. It involves finding a series solution about an ordinary point. We're asked to show that x naught equals 0 is an ordinary point of the differential equation. And then we're asked to find the general solution of the differential equation, where y1 and y2 are two linearly independent series solutions centered at x naught equals 0. We also want to state the interval of existence of the general solution of the differential equation. And I guess we should say how many terms we want of each of those independent series solutions. So let's say that we want 4 non-zero terms of each of those solutions. So we first want to show that x naught equals 0 is an ordinary point of the differential equation. So we look at the coefficient of the highest order derivative here. The coefficient of that highest order derivative is p of x, and that's equal to 1. So it doesn't really matter what x naught is. P of x naught is equal to 1, which is not equal to 0. So all real numbers x naught are ordinary points of the differential equation. Or if you prefer, you can evaluate this at x naught equals 0. And that's clearly not 0. So we can say from that that x naught equals 0 is an ordinary point of the differential equation. And we've done that first part. Okay. And I will just use OP as an abbreviation for ordinary point. Okay, then we're asked to find the general solution of the differential equation, where y1 and y2 are two linearly independent series solutions centered at x naught equals 0. So in order to do that, we're going to let the sum as n goes from 0 to infinity of c sub n times x to the n be the form of our solution y. And we just substitute into the differential equation, and we'll find the values of the constants that will cause this function to satisfy this differential equation. So we're going to let y equal the sum as n goes from 0 to infinity of c sub n times x to the n. Remember, that's c sub 0 plus c sub 1 times x to the first plus c sub 2 times x squared plus c sub 3 times x cubed plus c sub 4 times x to the fourth, and so on. Then y prime is the derivative of that. So you bring the constant down, and then you just use the power rule for the x to the n. So you've got n times x to the n minus 1. When n is 0, we're going to get 0 here. We want to start with the first non-zero term. So we're going to increase that index so that it starts at 1 instead, and then that will be non-zero. And then we are looking at a second order differential equation, so we also want to compute y double prime. So we bring the constants down, and then you use the power rule for the x to the n minus 1. So you've got n minus 1 times x to the n minus 2 there. And then when n is equal to 0, we get 0, and when n is equal to 1, we get 0. So the first non-zero term occurs when n is equal to 2. Then we want to substitute into the differential equation. And I would distribute in that differential equation first. So our differential equation is this. It's y double prime plus x times y prime. And then here I've got a y times this binomial. I would distribute that y so that you're writing it that way. So our differential equation has 4 terms, and each of those is going to be an infinite series, a power series. So assuming that y is in the form of a power series, then y double prime is equal to the sum as n goes from 2 to infinity of c sub n times n minus 1 times x to the n minus 2. And then we're adding x times y prime, and that's the sum as n goes from 1 to infinity of c sub n times x to the n minus 1. And then we've got 2x times y, and that was the sum as n goes from 0 to infinity of c sub n times x to the n, plus y. It's the sum as n goes from 0 to infinity of c sub n times x to the n. That equals 0. Now you've got 4 infinite series that you need to add together, but before you do that, you need to distribute the x to the first here and the 2x to the first here into these series. Now, whenever you multiply a series by a constant times the power of x, it's just like multiplying a polynomial by a constant times the power of x. You're going to distribute that constant to every term. So we'll multiply all the terms by 2 here. And you're also going to multiply the x to the n, each power of x, excuse me, by this x to the first power. What that does is it increases the exponent by 1. And that makes sense since x to the first times x to the n is x to the n plus 1. The same thing happens here. So when I distribute that x to the first inside this summation, what I get is c sub n times x to the n minus 1 times x to the first. And the x, when you add the exponents, you get an x to the n there. Over here, I'm distributing the 2. Then x to the first times x to the n is going to be x to the n plus 1. Okay, so we substituted into the differential equation, and now we've got 4 series that we're adding together, and that equals 0 on the right-hand side. In order to add these series together, basically we want to collect like terms, but the only way to collect like terms is if all series begin with the same power of x. So we want to remove terms from the series so that all terms begin with the same, or all series begin with the same power of x. So to figure that out, we will look at this series and figure out what it starts with. When n is equal to 2, we have an x to the 0 here. So this is going to start with an x to the 0 term. This one starts with an x to the first term. So when n equals 1, we get x to the first. This one starts with an x to the first as well. And then when n equals 0, this one starts with an x to the 0. An x to the 0 term. So all of these have an x to the first term. When n is equal to 3, this gives me an x to the third. When n is equal to, or excuse me, when n is equal to 3, this gives me an x to the first. And when n is equal to 1 here, we get an x to the first. So they all have an x to the first term, but there is no x to the 0 term in this series or this series. So we have to take out the x to the 0 term from this one and this one, so that the remaining series all start with x to the first. So we're going to remove one term from the first series and the fourth series, so that all terms, or all series, begin with an x to the first term. Okay, so the n equals 2 term is our x to the 0 term here. So when n equals 2, we get c sub 2 times 2 times 1 times x to the 0. And then when n equals 3, I'd get c sub 3 times 3 minus 1. So 3 times 2 is 6. 6 times c sub 3. And so 6 times, I would have 6 times c sub 3 times x to the 3 minus 2, which is x to the first. So when n equals 2, we get the x to the 0 term. When n equals 3, we get the x to the first term. And then when n equals 4, we'll get the next one, and so on. So After I take out that n equals 2 term, I will write the series in exactly the same way as it was written before, except I want to pick up where I left off. If this is n equals 2, I want to start at n equals 3. These two together form the original series. Now this one and this one already start with x to the first, so I'm just going to rewrite those. I'm not actually doing anything to those. Oops, I forgot the n. There we go. And then this one does not start with the right term. It starts with the next to the 0 term. So we'll take out the n equals 0 term. And then the next term will be the x to the first term. So that's where our series will start. When n equals 0, we have c sub 0 times x to the 0. When n is equal to 1, we'll have c sub 1 times x to the first. So we just write the series in exactly the same way as it was written there, except instead of starting with n equals 0, we start with n equals 1 because that's just the rest of the series. Okay, so now all the series start with the same power of x. I'm going through my pencil cup trying to find a blue Sharpie pen. That's my first series. This is my second series. This is my third series. And the fourth series was this term plus this. So now all 4 series that are remaining after we modified those first 4 series all start with an x to the first term, but they don't look the same. I would really like them all to have the same form, so that we all start counting at the same place. When n is equal to 3, we get an x to the first here, but when n is equal to 1, we get an x to the first here. N equal to 0, we get an x to the first here, and n is equal to 1, we get an x to the first there. And it's great that they all start with x to the first, but the counters are off. So in order to add those together, we need to make it so that the counters start at the same place, or alternatively, we need to make these exponents that we have here look the same. So in order to make the exponents look the same, we're going to relabel some of the series. So we look at the 4 exponents that we have: n minus 2, n, and n plus 1. And we say, okay, we've got 2 of them that are already n's. So to save ourselves some work, let's make these 2 series look like these 2. And then we'll be able to add them all together. So we're going to relabel the indices. So that all series here look the same. Or let's just say all exponents are identical. Okay, I want this n minus 2 to look like an n. So I'm going to let n minus 2 equal something. Now, typically I would let it equal n, but obviously n minus 2 can't equal n. So we're going to change this variable. We want to make it look like this, but instead of using n, we need to use a different label. So we're going to call that k, and then we solve this for n. If n minus 2 is equal to k, n is equal to k plus 2. Okay, so these guys are already fine, but we want to switch from the n's to k's. So on this second series, I'm going to let n equal k. And on the fourth series, I will let n equal k. And so then I'll write this series in terms of k, and I'll write this series in terms of k. Then on the last one, I want to take the exponent I have and set it equal to the exponent I want to have. And then I'll solve this one for n as well. If k is equal to n plus 1, n is equal to k minus 1. Okay. And let's group like terms in x. This is a constant term and that's a constant term. So we'll add those together, 2c sub 2 plus c sub 0. And then over here, here, and here, and here, we want to write those in terms of k rather than n. So when n is equal to 3, k will equal 3 minus 2, which is 1. And then every n here can be replaced by k plus 2. So this is c sub k plus 2 times k plus 2. K plus 2 minus 1 is k plus 1. And then this is going to be x to the k by design. So that's our first series. Our second series is going to look exactly like it already does. You just replace the n's with k's. And then the third one, instead of starting our sum at n equals 0, we want to start the sum at a value of k. When n is equal to 0, k is equal to 0 plus 1, which is 1. And then over here, I've got 2 times c sub n is equal to k minus 1. And then here, my n plus 1 is equal to k. So this is going to be an x to the k. Now, if you're wondering to yourself, okay, how is this really working? Notice that I'm increasing this by 1, while at the same time decreasing this by 1. So increasing this by 1 works as long as I decrease all of these by 1. And the same thing is true over here. I want to decrease this by 2. And if I decrease this by 2, it'll be exactly the same series if I also increase all of these by 2. And that's what this substitution is telling us. Now, if that didn't make sense, don't worry about it. You can just do the algebra. And then for the last one, we've got to just replace the n with a k. So if the sum as k goes from 1 to infinity of c sub k times x to the k, and that equals 0. Okay, so now they all have x to the k's. They all start with k equals 1. So we can add those series together. So this is 2c sub 2 plus c sub 0 plus a single infinite series now. And I'm going to factor out an x to the k. So I'm going to add this coefficient of x to the k to this one, and this one, and this one. And so this is what we get. We'll have c sub k plus 2 times k plus 2 times k plus 1. And here I've got a c sub k plus a c sub k, or c sub k times k plus a c sub k. So I think I'll factor out a c sub k from those. So that'll be c sub k times k plus 1 from those two. And then this one is just a 2 c sub k minus 1. And all of that is multiplying x to the k, which equals 0. Okay, so now I've got a constant, and then I've got this coefficient of x to the k for k equals 1, 2, 3, 4, and so on. Now we want 4 linearly independent series solutions, or excuse me, 4 terms in each of 2 linearly independent series solutions to the differential equation. So we are going to solve for these constants, these coefficients, but we would like to have at least 4 that depend on c sub 0 and at least 4 that depend on c sub 1. Now, if this is an infinite series on this side and this is equal to 0, because of the linear independence of powers of x, the linear independence of 1 and x squared and x cubed and x to the 4th and so on, because of that linear independence, if I've got these constants multiplied by the powers of x, and that's equal to 0 plus 0x plus 0x squared and so on, the only way that can happen is if all of the coefficients are 0. So the coefficients on this side have to equal the coefficients on this side, which are all a bunch of zeros. So we're going to set the coefficients on this side equal to 0. And then in each equation, we're going to solve for the coefficient with the largest subscript. So let's do that. So for my constant term, I've got 2c sub 2 plus c sub 0 is 0. And we want to get c sub 2 by itself. So we're going to subtract this from both sides and divide by 2. Now on this one, we want to solve for the one with the largest subscript. So that's a c sub k plus 2. So I will subtract this guy and this guy from both sides. And then divide each of those by k plus 2. Actually, let's divide the whole thing by k plus 2 times k plus 1 to get that c sub k plus 2 by itself. This is for k equals 1, 2, 3. It's always starting at the value of the index in that series and then increasing. Now, when we take each of these and we solve for the coefficient with the largest subscript, c sub 2 in this case, and c sub k plus 2 in this case, what that does is it allows us to find this in terms of coefficients that came before it. So as we substitute different values of k, we're building up our list of coefficients. And since we have written every coefficient in terms of coefficients before it, we can simplify each of those as much as possible. That's why we've got to solve for the one with the largest subscript. So we already know that c sub 2 is negative 1/2 of c sub 0. We need to find 2 more that depend on c sub 0. And then we need one more coefficient that depends, or 3 more coefficients that depend on c sub 1. So let's substitute k equals 1 and see what happens. When k is equal to 1, we get c sub 3 equals negative c sub 1. When k is equal to 1, we have 2 over 3 times 2 here. Those are going to cancel. K is equal to 1, that's going to be a 3. And then over here we have minus, when k equals 1, c sub 0 over, when k equals 1, I have 3 times 2. Okay, so it looks like we've got 1/3, negative 1/3 c sub 1 minus 1/3 c sub 0 is c sub 3 there. When k is equal to 2, we get this, c sub 4 equals negative c sub 2 times 3 minus 2 c sub 1, all divided by k plus 2 in this case is going to be 4, and that's 4 times 3. So we're going to end up with negative 1/4 c sub 2 minus 1 over 6 c sub 1, and negative 1/4 c sub 2 is negative 1/4 of c sub 2, which was negative 1/2 c sub 0. So we can substitute that in. So we get 1/8 c sub 0 minus 1/6 c sub 1. Okay, so I've got 1, 2, 3 coefficients that depend on c sub 0 plus the first one that depends on c sub 0. So I've already got 4 coefficients that depend on c sub 0. And I want 4 that depend on c sub 1. So I've got 1 here, 2 here, and, or no, I got 1 here and another 1 here. So that's 2 so far. We automatically get the first one. So I just need 1 more that depends on c sub 1. So k equals 3, let's see what we get. We got c sub 5 equals negative c sub 3 times 4 minus 2 times c sub 2, all divided by 5 times 4. And this ends up being negative 1/5 of c sub 3 minus 1 over 10 times c sub 2. And c sub 3 was that expression there. And c sub 2 we had earlier. So c sub 3 was this, negative 1/3 c sub 1 minus 1/3 c sub 0. And c sub 2 was negative 1/2 c sub 0. So we'll get 1 over 15 c sub 1 plus 1 over 15 c sub 0 plus 1 over 20 c sub 0. And I guess we need a common denominator. For these two guys, it's 1 over 3 times 5 plus 1 over 4 times 5. It looks like I need to multiply this one by a 4 over 4 to get a common denominator. And that works as long as I multiply that one by 3 over 3. That's multiplying c sub 0. I've got 1 over 15 times c sub 1 plus 7 over 20 times 3, which is 60, c sub 0. Okay. So we saw when k equals 1, we get c sub 3. When k equals 2, that allowed us to find c sub 4. When k is equal to 3, we were able to find c sub 5. And now we have enough coefficients that depend on c sub 0 and c sub 1. So we're going to substitute the coefficients that we have into the form of y. This could go on indefinitely. Now y was equal to the sum as n goes from 0 to infinity of c sub n times x to the n. So we'll have c sub 0 plus c sub 1 times x plus c sub 2 times x squared plus c sub 3 times x cubed plus c sub 4 times x to the 4th, and so on. Now c sub 0 and c sub 1 are fine. We're going to leave those alone. C sub 2 is negative 1/2 c sub 0. We're multiplying that by x squared. And then we're adding c sub 3 times x cubed. Well, c sub 3 ended up being negative 1/3 c sub 1 minus 1/3 c sub 0. And then actually, let's go all the way out to x to the 5th because we had a c sub 5. Now we want to add our c sub 4 times x to the 4th. And c sub 4 was from up here, this 1/8 c sub 0 minus 1/6 c sub 1. And c sub 5 was that last coefficient that we found, 1 over 15 times c sub 1 plus 7 over 60 times c sub 0, and it's multiplying x to the 5th. Okay, and now we want to group terms that involve c sub 0. So I've got 1 here, minus 1/2 x squared, minus 1/3 x cubed, plus 1/8 x to the 4th, plus 7 over 60 x to the 5th, plus higher order terms. And then we'll group the terms involving c sub 1. So I've got an x minus 1/3 x cubed, minus 1/6 x to the 4th, plus 1/15 x to the 5th. That's my 4th term that depended on c sub 1. So I've got 4 terms in that series, and that is our general solution. And in order to determine the maximal interval of existence, we can look at the original differential equation, and that was this in this case. And typically what we would do is if there were a coefficient of y double prime here, and we would divide by it, and then we would look at the coefficients of y prime and y and see where the series, where the power series centered at x equals 0 for each of those expressions would be well defined. But since there's just a 1 here, the quotient of, if we're calling this p of x times y double prime plus q of x times y prime plus r of x times y equals 0, the quotient q over p in this case is just x, and the quotient r over p is just 1 plus 2x. Well, those are both polynomials, and we can think of polynomials as power series. They just have coefficients all equal to 0. This one has all coefficients equal to 0, starting with the coefficient of x squared. And this one has coefficients of 0 for c sub 0, for the constant term, and all the powers of x other than x equals 1. So the power series expressions for these that are centered at x equals 0 are going to converge for all real numbers. So these are analytic functions for all real numbers. And that means they converge for all real numbers. So this series, or these two series, should converge for all real numbers. So the interval of existence is -infinity to infinity.